Yeah, thank you, Markus. Also welcome to this term's offensive security course from my side. Before we start with the actual talk, I'd like to make a quick announcement. My name is Karsten Nohl. I work for G-Data, that's an antivirus company located here in Bochum. And we are supporting this course since a while now. And by supporting, I mean we are offering an additional evening event in the rooms of my company, which basically means we will have some dinner, we will serve some drinks, and offer a cozy atmosphere, a cozy location, where we hopefully have nice and interesting discussions afterwards. So if you are interested in talking to Karsten in detail a little bit about the topics he's presenting today, or if you want to get in touch with people working in antivirus industry, or perhaps some of the organizers of the Hacker are also there. People from the CTF group usually join us. So if you're interested in having a nice time together with us, all of you are invited. And yeah, here you can see some facts, but if you're interested in joining us today or one of the other days, we are offering this event. Basically, every time we have an external speaker here, we will offer this event. Don't hesitate to come to me after the talk, and I can give you a little bit more detail. So, without any further delay, welcome, Karsten.
Yeah, thank you very much. Honored to be here. Nice to be back at school. I've been out of grad school for about as long as I was in grad school. And I want to use this talk to do something slightly different, to reflect the two perspectives. The one that I gained as a researcher in grad school, and the one that I'm now gaining as an industry-funded researcher. We have a hacking research lab in Berlin. 17 people right now who are focusing on disclosing vulnerabilities in widely used products. And oftentimes we can use the results to help companies improve their products. So we are somewhat forced to stay relevant from industry. That means that sometimes we're not so relevant for academia. And I want to bridge the two views today and perhaps give you a little bit of insight into what industry considers risks. Perhaps the one question I'll try to answer for a lot of you that you'll have asked yourself over and over again, having seen academic research versus what actually happens in the world, is why does industry allow so many vulnerabilities to exist? Why don't they just fix it? Right? That's basically what every researcher ask themselves 2 years, 3 years, 4 years after they discovered the vulnerability, and they see that it's still out there in the world. And the same happened to me over and over again, but also some of our research did get fixed pretty quickly. And perhaps I want to find some structure behind that and share the insights that I think we gained through working both academically and with industry. I'll walk through a total of 5 examples, 4 out of my own research, and then one from the other side, from the areas of RFID chips and mobile security. Before that, though, I want to give a very quick primer just to build a mental framework for what I mean by risks and how different groups of people seem to be talking about risks differently. In academia, it often happens that you think of risks as the technical vulnerabilities that you find. If you can show that a widely used algorithm, for instance, is broken, you consider that a risk right away. Write your paper, it gets published, and that's when you start asking yourself, why don't they remove that risk? In industry, it works a little different, and if you've ever seen kind of a risk management, they usually do this in Excel sheets. I was asked the questions of how likely is something to happen and how much damage is it going to cause us. And this logic comes from business continuity management and is kind of moved into the IT security world. So in business continuity management, you think about stochastic events, let's say snowstorms or floods, things where you can look at the historic sample set, and you can extrapolate the likelihood of certain events. You can estimate the likelihood of a snowstorm this winter that will perhaps cut off electricity, right? So there's a, leaving global warming aside, there's a reasonable chance of guessing the future by just looking at the past. And that's how they fill in this probability field. Now that doesn't work at all for hacking. I mean, most likely the next attack that's going to take out the major infrastructure will be one that has never happened before. And the one after that will be new again, and the one after that will be new again. There's constant invention. There's a dynamic adversary, somebody who thinks through mind games. Where are you most vulnerable? What is the one thing that you never considered happening to you? And then they'll make that happen. So from my perspective, that probability field, when they type in all the IT security risks, is always a guesstimate and oftentimes wrong, right? However, the logic, of course, applies. If you could estimate this properly, that's actually what the risk is. If something does happen regularly and it does cause damage, that's exactly what you want to prevent, right? So I think a third view is needed to actually bridge these two worlds, and that is actually the person who's going to cause the damage, who has a reason to cause the damage, and that's the hacker. Things are unlikely to happen, especially in this very dynamic, adversarial-driven world, when nobody wants them to happen. And they want them to happen for various reasons, but oftentimes to gain money or to send a message. You know, think of Anonymous, for instance. It's unlikely that just because it's possible that something is going to break down, it will happen. And it only becomes a risk then if somebody in the world is interested in making it happen, if somebody, for instance, makes money. Also, what's needed is a technical vulnerability. That's exactly what academic researchers regularly find. But also what it takes to be considered a risk is a downside to it, right? And we'll talk through a couple of examples, and oftentimes the downside happens to somebody who isn't actually in a position to fix it. For instance, all these privacy intruding attacks that my research has been covering. The companies who are in the position to prevent your privacy from being intruded on, they have little interest in doing so because the damage is with you and not with them, right? So this is the model that I want to think in. That I want to take a hacker perspective, a research perspective, and an industry perspective at the same time, and revisit a couple of research results, and then perhaps explain why some of them got fixed and others haven't. If there's any questions throughout, just raise your hand, right? I'll pull you up then when I have time. Any questions so far? Everything clear? Okay. So let's look at RFID chips. These make for great examples of vast vulnerability and little movement in the industry. This is technology that even when I looked at it 5 years ago was already ancient. Some 15 years ago, it was invented. So now we're looking at some chips that are commonly used and billions in numbers that are 2 decades old. And let's start where I started with my research journey. This is during my first year in grad school. I wanted to look at, with a couple of friends at the Case Computer Club in Berlin, at a popularly used RFID chip. And this one had been given out some 4 or 5 billion times. So statistically, everybody had used one of them already at that point, in bus tickets, for instance, or in building access control. And we got hold of a couple of these chips, tiny, tiny chips. And next thing I know is I'm taking a chip design class because I wanted to understand what all these structures were. We cut out a little bit here and then zoomed in. So there's all these metal structures and whatnot. And I took this class that taught me how I would build a chip, you know, etching away and depositing material to create structures that then encode logic. We took pictures of the different chip layers, kind of reconstructing what somebody who did design this chip laid down, and then started reverse engineering what functionality could be behind that. Created in the process some software. I started with MATLAB scripts, a much more talented programmer created this software that we today use for these projects. It's open source, so everybody's free to have their go at reverse engineering a chip. And basically what this does is it traces all the connections between logic cells, is what they're called. And then in the end outputs basically an assembly language description of the chip, but with much more parallelism than a software assembly. So different instructions, of course, can happen at the same time in a chip. And so the logic flows are much more complicated than in software. But in the end, this is just commands that are executed one after another. And from that, we could reverse engineer the cryptographic algorithm. It was a pathetically weak stream cipher, where if you had some key stream, cipher stream, you could break this on maybe this laptop in 2 seconds, I would say. Right? And again, this is used in billions of chips across tens of thousands of applications, predominantly bus ticketing, but also some higher value applications like access control to buildings of the German army, for instance. Now, that result got all the press. That we said there's a bad cryptography used with billions of copies out there, and the manufacturer is pretending that this is secure. And we found ourselves in kind of a press cat and mouse game where NXP, the manufacturer, kept emphasizing how this was not actually creating a risk. How we, yes, found a technical vulnerability, but we didn't actually expose anybody to risk. There was very little chance that people would take this result and then conduct a criminal activity, as in copying a bus ticket, saving a few euros, or at most maybe saving a monthly subscription to a bus line. Right? And today, I think I tend to agree with them that the risk was totally overblown. Of course, back then, NXP also emphasized that this is not used for things like access control, and a lot of governments found themselves actually using it for access control. So the discussion was a little two-sided, but for the most part, they were right. We found a technical vulnerability and got a lot of press for it, where really there was no risk. The risk did come later based on another research result on the same topic. Somebody looked at the protocol a little closer. And it's a very simple challenge response protocol. The reader will open up the chip by sending a random number, as well as an encrypted version of that random number. And then the chip will respond with yet another encryption of a slightly different random number derived from the first. Right? And if you take out the reader from this equation, if you only have the card, there's little you can do to the card, because it expects some well-formatted, here's the random number and here's the encryption packet from you before it even starts talking to you. So that's why NXP kept emphasizing this is not really a risk. You have a card, let's say bus ticket, you cannot make a copy from it unless you have a reader. So take your own card to a reader with a sniffing device, you intercept all of that, you copy your own card. Granted, that's possible. It's kind of harder to do it to other people. You'll have to install a device next to the real reading device. It all gets complicated. Basically, that's what their defense was. Turns out, though, it's not quite so easily cut after all, though. In addition to the random number and the encryption of the random number, what they do send along is parity bits, 8 parity bits, basically checksum, so that the RFID tag can distinguish 2 different cases. One, that the authentication was actually wrong, and the other, that the authentication may have been correct, but it got disturbed during transmit. This is unreliable wireless communication. So there's 3 cases overall. There's a bad parity in an other, so there's bad parity. There's bad authentication with good parity, and there's a valid frame. And the tag does behave differently based on those three. So it doesn't just have a fail and good case. It has a, what you sent me has correct parity bits, but the authentication is wrong nonetheless case. And it will respond based on that. And given that this is 8 parity bits, in 250 cases, if you just send random data to it, it will respond once, giving you information about what it considers valid parity bits. And it will even respond with an encrypted error message. So in this case, the tag doesn't stay silent, which it's supposed to do if you can't properly authenticate to it. It will give you 8 encrypted parity bits. It's kind of confirmation that they were correct, plus 4 bits in the response, 12 bits. So you need 5 of those to reconstruct the key. You send a couple thousand just randomly chosen queries to the tag. You can derive the key, again, within seconds. And this second bug moved this attack well beyond you can copy a card at a reading device to you can copy just any card, maybe of somebody sitting next to you in the subway. So that, in the end, created the criminal business cases. Not maybe around bus tickets, but definitely around building access control. Just by being in the vicinity of somebody, now you can steal the access credentials, right? So it took 2 bugs to break this technology. And finally, a lot of people are moving away from MyFair based on that second bug, based on the understanding that no cameras and no monitoring of their reading devices is going to help them because the cards themselves are vulnerable. And there is a lot of movement right now, especially in the access control industry, to move past this MyFair technology. So all clear, right? They could have prevented bugs on 2 layers. One is actually somewhat complicated. This is 20-year-old technology. How do you put a good encryption function in a tiny chip? It's probably going to get bigger, hence more expensive, or the reading distance goes down because it takes more electricity. So it may be somewhat of a trade-off, and maybe they intentionally made the trade-off to have a not-so-good encryption function. The other bug, though, that's a no-brainer. There's no cost to not doing that. It's absolutely unnecessary to encrypt error messages. It's absolutely unnecessary to encrypt parity bits. All of this opens the chip up to hacking. And this got little to no press, right? So it seems that, that the criticism didn't go far enough. And if somebody today builds an RFID chip, they'll claim that they use a good encryption function. Nobody's up to prove that they put this encryption function in a well-designed protocol and implemented this protocol for the chip to not act stupidly like this one does, right? So what I'm saying is security is oftentimes much more convoluted than it seems from the outside, and the vulnerabilities are often pointed out quickly, but really there's a much deeper story to them. Let's move on to a similar vulnerability in a related technology, and that is car immobilizer chips. So those are also RFID chips, and they're pretty much in every car key for the last 10, 15 years. So basically every car key that has a plastic portion to it has a chip inside. Back in the day, you had metal-only car keys. Those all but disappeared. And this is a very successful technology. It brought car theft down considerably. Only in the last couple of years, it's back up. And these chips, they work on a very similar concept to the MyFair chip. The authenticator, who wants proof that the right key is there, in this case the car, sends a random number. The car key encrypts the random number, sends it back. So at that stage, the car knows the right key is present, and the immobilizer protocol could be done. But they add a little bit more to have extra functionality. So they also authenticate the car to the key. And this will be important later on, because somebody screwed this up. But in this very basic form, the same protocol is done the reverse way. The key sends a random number to the car encrypts it, and now both know that they can trust each other, And the car can, for instance, and that's why they do the second step, write current car information onto the chip. And that's actually done. So whenever you start your car, the car puts the current mileage onto the chip, so that if your car gets stolen, your insurance company can read out the mileage from the key that hopefully you still have. Right? So that's how they estimate the value of a stolen car. They need the mileage. And that idea opens at least one of the technologies up for attack. There's 3 technologies that really dominate the market. There's one by Texas Instruments using a 40-bit cipher. There's one by NXP again, a very related technology to that MIFARE chip, just for a different purpose. 48-bit stream cipher, just like MIFARE, but a slightly modified cipher. And then there's a Swiss company that builds this Megamos chip, 96-bit. That's predominantly used by the Volkswagen family, but also a few other mostly Asian brands. And all those 3 are broken in different ways. The first one, the 40 bits, was broken when I just started grad school, 2005. Somebody at Carnegie Mellon put together a couple of FPGAs, and they just brute forced the entire key space within an hour. Right? So 1 hour later, you can copy, in this case, a little payment device that used this DST chip, and then go pay for gasoline, in this case, in the US. Now, this attack doesn't scale even to the next in line, the 48-bit NXP. So 8-bit more, 250 times more complexity. That means you'd have to have 250 times this stack of hardware, right? Probably not worth it to steal cars or whatever your intent. However, the NXP one is breakable in a completely different way. This one also, but this is the attack published, and I guess it's good enough. So the NXP one is breakable more based on its inner structure. So this is breakable based on its key size and nothing else. And the inner structure of this high-tech 2 cipher is mostly an LFSR, linear feedback shift register, where bits get kind of rotated around and XORed with each other for a good number of times. And then once you kind of shook this for long enough, you then take a sample, put it through an output stage, and that's your key stream. And this violates what I would see as a base requirement for stream ciphers, that is good nonlinearity. And the attack, let me describe the attack perhaps, and you'll see what went wrong with this cipher design. The attack that we'll do starts by describing this entire computation from the output bits all the way through the shaking and then through the output stage in equations. That describes every output bit in terms of input bits or combinations of input bits. And we don't want to do this algorithmically, but statically. So we want for every output bit, one line that describes in terms of input bit the entire correlation, right? And we'll only allow ourselves few symbols. So the standard methods do AND and OR. So you have either ANDs of ORs or ORs of ANDs, and it will look something like, so the first output bit is, let's say, X1 and X3 and X4, and then there's a few more, let's say X1 or X2 or X4, and then it can go all the way up to X1, X2, up to X84. There's 84 input bits here, right? And these terms can be there or not. You see the X2, for instance, is missing. It's not there, some others are there. And there's a total of 2 to the 48 different terms that can be in this equation. So if this is a well-designed cryptographic function, it will actually make use of this potential of these 2 to the 48 and have roughly half of them in it. If you compute this or try to compute these for AES, you'll find that it actually has an almost perfect distribution across these terms. And if it really does have this, even computing this equation is as expensive as brute force, right? 2 to the 48, that's exactly the brute force complexity. So a vulnerability only arises if you could compute these equations much faster. So if of the potential 2 to the 48 terms, much fewer are actually used. And with LFSRs, that actually is the case. So back when we researched this, we took a linear, not linear, like a standard equation solver, a set solver, and modified it slightly. In addition to the AND and the OR symbol, we allowed the XOR symbol. To change the solver in a couple of places, but we kind of extended the description language. And if you allow the XOR symbol, and if you look at the LFSR, every output bit of the LFSR will always be an XOR combination of input bits. Something like this. And there's at most 48 such terms. And if you want to throw in one more, beyond the 48, you cancel out an existing one. That's how XOR works. So at most, your equations are 48 terms long now. Makes sense, right? And this is the LFSR. And I said, after the LFSR, they do a little bit of output stage, so it becomes a little bit more linear than this. But in the end, it's still very far from 2 to the 48. Meaning we can actually spell out these equations for high-tech 2. And the reason that's possible is because it's mostly linear. It doesn't accumulate nonlinearity. It doesn't take these terms and end them together or OR them together to create bigger and bigger and bigger terms. It only does it once in the end. And we spell them out, and we throw this modified set solver at them. And then we do what I want to call smart brute force. It's kind of hard to see, but you see the general structure. It's kind of like a wing. So actually, maybe I can zoom in here. How do you zoom in? There was one key you could press here. Oops. Yeah. So you see what this is? So it's this is a visualization of a solving of this high-tech 2 in the set solver. And it works the following way. You have these equations that you wrote out. One for every output bit, so 48 total in this case. And now you start randomly guessing terms, just like brute force. You start guessing bits, right? You guess that x1 is 0, let's say. 0 is always good because then it goes away. So you guess that this is 0. And a couple of these equations will simplify, right? And then you guess the next one. Let's say you also guess that x2 is 0. And they will simplify further. And these equations, they shrink and shrink and shrink. And you keep guessing, and they keep shrinking. And eventually, you'll derive at a contradiction. Some of these equations will have shrunk to terms that are simple, but that contradict each other. So that's when you know you guessed something wrong. Right? One of the guesses is wrong. And you don't know which is wrong, but you know that this set of guesses you made up to this point cannot be correct together. And you remember that in the set solver. And that's how this is different from normal brute force, where you just move on to the next try and forget everything you did so far. You remember that when you guessed all but one of the bits in this set that you guessed previously, that let's say x1 is 0, that cannot be the right next guess. It must be the other one, or neither. But you prune branches of this brute force tree. And this picture illustrates how many branches you prune. So as I said, it starts up here, and it guesses 1, then it guesses 2. Let me zoom out a little more. Then it guesses 3, 4, 5, 6. And when you count them down, it guesses about 40 bits. Until it reaches the first contradiction. And then it backtracks, what it's called, and it searches for the first, it basically takes back guesses, kind of every time taking a state it previously had, it remembered all of these, and it tries the other guess, right? And up till it reaches the next contradiction. And as you see from this shape, through learning, that certain sets of guesses should not happen together, it doesn't ever have to go all the way back down here. It can learn quicker that things are implausible. And it guesses maybe 35 and then mostly 20 or so guesses. And it gets better and better and better until it understands a lot of things that are not the solution and accumulated all this knowledge. And then it's getting better at guesses, partly by chance, but partly just because there's not so much left of the brute force space. And it's getting hotter and hotter as it keeps guessing things down here, and eventually it guesses everything correctly based on the knowledge that kind of guided it through this brute force tree, right? And if you count up the number of operations that it did, basically everything that's on this slide, that's a couple of thousand operations. And each of them, of course, is more expensive than one computation. There's this big data structure that you have to evaluate, you shift things around, but still, a couple of thousand somewhat expensive operations versus 2 to the 48 simple, right? That's still many orders of magnitude faster. And that's why we don't need 256 stacks of FPGAs to break this, but one computer about a minute, right? Through smart brute force. And why is that? Because the high-tech 2 doesn't have enough algebraic complexity. So again, this result got published, and not just this, but a couple of follow-on papers that keep beating that high-tech 2 get a lot of press. So about once a year, somebody publishes a cars can now be stolen paper based on these vulnerabilities. And you'd think that a lot of cars did get stolen. This is so easy. We open source the software. Everybody can do that. Also, everybody can buy 5 FPGAs and does the Carnegie Mellon attack. However, not a single car got stolen based on these vulnerabilities. And why is that? Because of the protocol we looked at in the beginning. The car sends you a random number, and you're supposed to encrypt the random number. If there is no key, and you break into a car, all you see is a random number. And you can ask it again, and it will send you another random number. But it doesn't matter what the encryption is that's supposed to happen next. If all you see is a random number, there's no way of stealing a car. You see how the academic perception of this is terrible, and how could they put this in hundreds of millions of cars versus the reality. All you get is a random number. It doesn't matter what the encryption is, how they really divert. Now, they don't divert, interestingly enough, for the third on the list, Megamos. And this is an interesting one because it's so much better than the other ones in any academic sense. It was a bitch to reverse engineer. It took us months looking at these pictures in degate to figure out the algorithm. And then it took us many more months to adapt our set solver to also solve Megamos. In the end, though, it was the only one worth even pursuing that because Megamos changed the protocol. Megamos said, why have a 3-way handshake if we can package the first and the third into one? If we can, while sending the random number to the key, at the same time prove that we are a legit car. Remember, they need to do that because they want to write information into the chip, mileage and so forth. So they compress a 3-way handshake into a 2-way handshake. So if you approach a car that just has a Megamos chip, it will give you encrypted random numbers, not just the random numbers. And that's what you can use to break it. Right? So even though people keep emphasizing how terrible all these immobilizers are, only the one that gets it mostly right, that's almost unbreakable, at least after spending months of it in a set solver, and that's a lot of effort, and I don't think many car thieves would go through that. So it's barely breakable, and it's the only one that actually constitutes a risk. Right? Industry seems to agree. So all the high-tech 2 papers, they went totally under the radar. When somebody who gained these Megamos results independently from us tried to publish them this year at Usenix, they got sued in the ground by Volkswagen. Right? Like, I cannot believe that any judge would side with Volkswagen, but the court in England disallowed University of Birmingham from publishing these results. Right? There was some weird argument around they reverse engineered it from a piece of software that some car thieves use from Bulgaria or something. I don't know. But so basically, a judge said this is too much of a risk for society. Right? So it must not be published. ridiculous. But that tells me industry sees a risk in here, where in the other technologies that were broken, they didn't see so much of a risk. And perhaps, you know, behind the curtains, they are working very hard to replace this one now, where the high-tech 2 is just allowed to live on forever, it seems, even though it has been broken over and over again academically. Again, big difference between a vulnerability and a risk. Any questions on this so far? No?
This SAT solver is satisfiability solver.
Yeah.
Okay, how this mapping occurs? I have these bits static that are used to compute the first bit, y1. Yeah. How do I map to make a SAT equation with the XOR?
Oh, this is a SAT equation. This is one right there. An ANS of ORs, or an ORs of ANS, is CNF basically, right? That's what you feed the SAT solver. And what we changed in the SAT solver that we use, it was called minisat before. We have a derivative that's called crypto minisat. We added in the XOR function, but it's still, it can also understand and OR. So that's what you feed it with. You can give it a long description, all these equations, and it will tell you whether there's a solution or not. In fact, this is used for many applications outside of cryptography. For instance, when you describe the layout of a PCB board, right? You say, is there a solution to route wires between those points, right, without intersecting? Or on a chip, if you want to connect certain logic cells and you only have limited area to route wires in between, you describe this in an equation and you ask the SAT solver, is there a solution to these equations that connect all the different points without intersecting lines, right? So the driving forces behind SAT solvers are companies like Intel, who are routing stuff on chips. But there is a competition every year, the SAT solver competition, I guess it's called, at the SAT conference. So it's a whole research community in itself. And we compete in it every year. And the crypto minisat, interestingly enough, wins every other year or so, at least in one category. They have very, very weird different categories. So that tells me that this XOR extension is not just beneficial for cryptography, where people like XOR because it has this beautiful symmetry, but it seems to be present in a lot of other real-world problems where people have just not seen it yet because they think in CNF, right? But yeah, it's still under development. And the guy behind it, Mateusz, he's on my team. He's eager to win the gold medal again. This is a cool research community. They give out gold medals, not just best paper awards. Any other questions on the RFID stuff? So
your paper never got to be published?
Oh no, it did. Yeah, it did. Yeah, I don't remember in what conference though. You see, I guess no. Wait, I can look it up later. I remember we did send it to crypto and we got really good feedback, and maybe then we sent it to Eurocrypt or something. Oh yeah, it did get published as, this is how you solve cryptography with SAT solvers. It's kind of the first idea in that direction. A couple of people wrote their PhD dissertations about that at the same time. So it was kind of an obvious idea. But we were lucky enough to find a cipher that has a real-world application and that was stupidly enough designed to actually be vulnerable to this idea, right? So this only works against stream ciphers, really. It's hard to mess up a block cipher to the point where it would be vulnerable.
Did the paper invoke any attacks?
Did the paper invoke attacks? Well, I think, as I described, there just isn't an attack potential. All you have to work with is a random number. So if you mean by attack somebody stealing a car, that's not possible. And there were at least 3 follow-up papers that broke the same cipher again, and all of them described no real-world risk. Okay, everybody got that, right? That was the main point, actually. Moving on to crypto in cell phones. 2 examples there. Well, 3 actually. Two out of my research, though. We wanted to show that cell phone calls can be intercepted, and we mostly wanted to show it because we understand that there's a market for boxes that do that, and we want to warn people about those boxes. And the market hasn't gone away, only the results have become more and more public. So hopefully, at the very least, we destroyed the market, and now there's a price competition or something. But here's what we looked at. GSM, the base technology still of all European and most other cell phone networks in the world, uses kind of an elegant key derivation scheme where from a master key that's stored on a SIM card, we'll look at SIM cards a little later, a session key is computed. So if you want to intercept a phone call, you'll have to break a fresh key every time for every phone call. And the same goes for SMS. At least the cell towers can use a different key every time. Some of them don't and kind of recycle them. At this stage, we were interested in breaking this session key. It's a 64-bit key. Now, breaking it on, let's say, a brute force machine, 64-bit, so that take on this Copacabana here a couple of weeks, that's one thing. But breaking it in a real-world risk sense would mean you'd have to break it within seconds. Because what happens in GSM is, among the first things it sends after it starts the encryption is a frequency allocation. It tells the phone where to go to, and it jumps between different frequencies to actually conduct a call. So only with that information, you can actually jump to the correct frequencies and then record the call. So if you only break the key when the call is already over, you don't get to record it. Right? Make sense? So we have a challenge here of having to break a 64-bit key that a brute forcer would take a couple of weeks. Break that in a second or so, okay? And there's a generic attack method that actually allows that for a lot of cryptography, not well-designed ones, but stuff like GSM. And that's called time memory trade-offs, or also known under rainbow tables. And it works on a principle of code books. So the base principle of a code book would be a data set where you compute the encryption of a message under every possible key, okay? And you note down the results. So you have all the keys in one column, you have all the results in another column, and you sort it by the results. The encrypted version, basically. Next time you see that encrypted packet over the air, you just look up in your data set what the key was. That's straightforward, right? But for a 64-bit key, that data set is a couple hundred petabytes large. So it's an obvious attack that's much faster than brute force, but it's resource intensive in another sense, storage in this case. However, these are only extreme points, brute force and the code book of a design space where you can trade off these two parameters. You can spend a little bit more computing power and have a little bit less memory requirements, for instance. And that's now the idea of time memory trade-off, or rainbow tables in the end. And the way these work is basically you start with the code book, you take all the input values, let's say the different keys, and you encrypt the message under this function k. So k is here the GSM function, let's say. And you encrypt it. And this would be the second column of your codebook. But you don't stop there, but you keep computing it. So you treat the output again as a key into the same function. You encrypt the message again, and you treat that as a key once again, and you keep going. Our data set has, they're called chains of a length of 1 million. And we only store the first column and the last column. And this data set now allows you to still find all the keys that were used at some point during the computation, even in the columns that you didn't store. And this is how. You see a message encrypted going over the air, and you look it up in this data set. And then, you know, in one of the millions, it is actually here, because you stored some of them here. In most cases, it isn't, though. Then you take that message, and you run it through this function k. And the output of that, you look up here again. Right? And if you don't find it yet again, you run the function on it again. And you kind of keep building this chain again backwards. right? And in this example, for instance, if your message was 2F06, you look it up, don't find it. You encrypt it once, don't find it. You encrypt it twice, this message encrypted twice, you do find it. You know what chain it belongs to. You start from the other value in the chain, recomputing it, and the value before this 2F06 is the key you're looking for. So it's a generic method to invert an otherwise non-invertible function. Right? Makes sense. It has two practical limitations, though. The first is collisions. If you keep growing this data set with a nonlinear function, like the GSM function, you'll end up having similar values, even though the input values were not the same. The same values mean that the rest of these chains become redundant. So it becomes very hard, if your chain is somewhat larger, to add new information. The new information will keep repeating old information. And so you'll never get an acceptable coverage to solve most GSM keys, for instance. The other limitation has to do with crack time. So the crack time of this should be really fast. All you have to do is compute up to 1 million chain links. And after 1 million, at the very latest, you find it in the last table. But also, and this is the limiting factor here, you have to look up in your data set 1 million times. And hard disks are much slower than CPUs. So 1 million computations on a CPU, that's milliseconds. 1 million hard disk lookups, that's minutes probably. Right? So both of those want to be solved. And were solved well before we even looked at this. The solution to this hard disk lookup, that's a pretty elegant one, and one that comes at no cost whatsoever. It's called distinguished points. You define a criteria for values to be allowed into this last column. And then instead of computing all your chains up to a defined length, you compute them up to reaching this criteria. So in this case, the criteria is the last 8 bits are 0. Right? And then you keep computing until you hit a value that has the last 8 bits 0. And some of these chains are short, some of them are very long. You may even end up in an infinite loop, then you just throw away the chain. But in the end, you have an equivalent data set, at least in coverage. So this will have a length of 2 to the 8 on average of chain lengths. Right? And so that means you keep computing, encrypting the message you saw on the air until you find one that has this criteria. Only then you look up on the hard disk. And that actually makes it an elegant attack. So it's a data set in our case of 2 terabytes. This lookup would still only take milliseconds on a CPU and 1 hard disk lookup, so still milliseconds. And that's too good to be true because we still have the problem of collisions. And those are solved using the actual rainbow scheme. The metaphor rainbow comes from moving from using the same function in every round to a slightly different function. It's called a round function or colored function. And so this can be as simple as just XORing in a value. So this can still be the GSM A51 function, XOR 1. This is the A51 function, XOR 2, XOR 3, and so forth. And when doing that, when using a different function every chain link, collisions only matter when they occur in the same column. If they actually occur in different columns, the remainder of those chains will be different again, right? So the probability of collision goes down to 1 millionth. And that then, in the end, creates an acceptable collision rate where we can actually compute this data set to cover most GSM calls. Now, this scheme also drastically increases the lookup time. So it's not milliseconds anymore, but something quadratically higher. And I'll leave that to the interested listener to figure out why. But so quadratic of milliseconds, that's then seconds. So we have terabytes and seconds on a computer to break GSM calls versus weeks on an expensive machine, right? And this is a generic function. This has nothing to do with how they implement it in GSM. You'd think that is the academic result that people could have pointed out years ago. I mean, you don't even have to look at GSM. it says in the specification 64-bit, and you know these time memory trade-offs exist, so you know it's broken. But it's not so easy. The risk comes yet again from a second vulnerability they put into the system. I made a shortcut in the beginning. Maybe some of you noticed when describing this codebook. I said you take a message and you encrypt it with every possible key. But what is that message? There's a very strong embedded assumption that every GSM call has a message. That one message that you can use to build the data set, right? And that's not true for most systems. Most systems will only encrypt things that are actually secret. So they'll be different for every transaction. It turns out, though, in GSM, about half of the packets they send out through the call setup, they're predictable or even static. So for instance, the cell tower, it will broadcast its identity twice a second, and the identity never changes. And maybe if they build a new cell tower, then they reconfigure them, but hardly ever will anything change. And they send these identities out unencrypted while encryption isn't switched on yet, and they'll switch on encryption, and they'll send out the exact same packet twice a second encrypted. Okay? So all of a sudden you have messages here that are completely predictable. And that is the real vulnerability that exposes these messages to cryptanalysis. Right? So again, a much under published fact that the real vulnerability here is in protocol design and not so much the bad use of cryptography. You can fix it on both levels, but introducing a stronger encryption function in the 80s during the Cold War probably was a harder choice than to just not fuck up your protocol. Right? Again, there's no cost to not doing it the wrong way. Right? In fact, again, industry kind of proves this point by having pondered this problem, not just since we published these results, but years earlier, some new standards were amended to the GSM standard, and they all tried to solve the second box. In fact, every single suggestion on making GSM better that has been published so far by academics or industry has been addressing the second box. So there's the suggestion to move to A53. That's a new encryption function. How long is the key? 64 bits. They didn't change the key size. They moved from a stream cipher to a block cipher, because that actually is 2 orders of magnitude more time memory resistant. Now, 2 orders of magnitude, that's just a couple of years in Moore's law, so eventually that's breakable again. All the other standard amendments have created unpredictability in the standard. So every time a cell now sends out its identity, they throw in a couple of random numbers so that the packet is different every time and is encrypted differently every time. Right? Tiny changes with gigantic effect. And so the criticism from the outside, 64-bit is bad, is not actually valid in terms of risks. It's what's behind it. It's what the protocol does with the 64-bit cipher that makes it vulnerable. Make sense? Moving on then to more recent work, stuff that we published this year, SIM cards. SIM cards have these magic capabilities that nobody is really aware of. Maybe some of you are, but most people think of SIM cards as exactly what I described in the earlier picture. Keeping a master key, very secret, and based on a random number, doing some key derivation and giving out a session key. So basically, SIM cards are thought as authentication oracles. And traditionally, that's where they're coming from. But today, that function is one of many processes running in a Java virtual machine on a complete operating system. And all these other processes, they do weird stuff like sending your location back to your network operator while you're in other countries. Supposedly also to the NSA, speculations now say. Who knows, right? So there's this whole computer running inside a little chip inside your phone that, on top of everything else, is remote programmable. So the network operator isn't even limited to the set of programs they gave you when you got the SIM card. They can put more programs on it. And it turns out the standard suggests a couple of different encryption functions. There's AES, there's triple DES, and there's single DES. And about half of the world's SIM cards use single DES. That's a 56-bit key. And as I said earlier, block cipher is about 2 orders of magnitude more time memory trade-off resistant than a stream cipher. So a 56-bit DES is about as breakable as a 64-bit GSM cipher, which is a stream cipher, right? So again, we compute rainbow table, same method, and again, we can break keys that are used to manage applications on a SIM card. Now, to explain how an actual risk arises from there, that's yet again on the protocol layer. So the real mistake, the exposing of this 56-bit crypto construct, is done on the protocol layer. And in a part of the protocol that's not actually specified. So everybody who implements SIM cards can do whatever they choose best, deem best. And people do make different decisions. So some companies got this right, some others screwed it up. And again, like in the MyFair example, it works on sending wrong stuff to a card. So in this case, every Java management packet is signed, or MEC'd, if you want to use the correct cryptographic term, with this 56-bit key. And if you send a management packet to a card that is signed with a wrong key, it's of course not processed. But the cards then behave differently on this packet. Some cards just throw it away, right? I got a packet that didn't authenticate, I'll throw it away. Some cards are nice enough to tell the sender, hey, you sent me something, but it was wrongly signed, right? Perhaps the network operators configured the wrong keys, and they're like a heads up that they should use different keys. So that actually makes sense. Some cards, though, they send back an error message and sign it with the 56-bit key. And since this is a MAC and not a signature, this is the same key used in the other direction. So the card signs something with the key that you didn't have to sign it, and you signed it wrong. But that's exactly the piece of information you need to put into the rainbow table to get that 56-bit key and then sign the next packet correctly. Right? So the standard says you're allowed to use a 56-bit key. And that's not so good. But the risk that actually opens up from that would be pretty minor. The risk would be something like if you happen to intercept a management SMS, that the real network operator with the valid key signs to the phone, then you can break the key from it, and you could send a second packet right after it. That's malicious. You didn't even have, you wouldn't even gain the phone number though, so it's kind of hard to know where even to send it to. It's an academic vulnerability, sure enough, and everybody else would agree that using DES is not good, but it's unclear what risk arises from that. However, now allowing people to remotely probe a phone number for this vulnerability, please send me a signed error message so that I can compute the key I need to put Java software on your card. That's a completely different story. And again, something that was completely unnecessary. So again, maybe at the first SIM cards, it wasn't so easy to get something bigger than DES into the smart cards. Maybe it was a cost issue, maybe an export issue, right? So today it should all be gone, but they just never changed it. Not sending a signed error message, that's absolutely no cost. That's a win-win decision. Nobody suffers. Nobody needs that signature. So I think the bigger scandal here is not that they use bad crypto, but that they use that bad crypto in a bad protocol. Okay? We're talking about SIM cards. There's actually not just 2 bugs, but it keeps getting worse. Once you are on the SIM card, this is just for 2 manufacturers now, but they're something like 70% market share combined. Once you are on the card with your Java, the Java doesn't do sandboxing well. You are supposed to be limited to some functions, and I'll show you which ones. And they are already pretty bad. You can send SMSs. You can dial phone numbers or change people's voicemails. You can query the location and send it back, maybe through SMS to whoever put the virus there. On some phones, you can even browse the internet. So that allows for all kinds of abuse, right? Click jacking or premium SMS fraud. You can spy on people. You can stalk them. But if that wasn't enough, you can then also break out of these APIs, become root on the SIM card, and, for instance, extract the master key. So that you don't even have to remote control the existing SIM card anymore. You can create an exact copy of it somewhere else. So that's the remote SIM cloning. And I don't know which threat exactly, anything on here, maybe the premium SMS fraud, or that remote SIM cloning, got the operators working on it, but they worked hard and fast. One operator that I know of, they put 400 people in a task force this year to solve this issue. 400 people. And now, ironically, we published this 3 years after the GSM attacks, but the solution is there earlier. The GSM stuff still is under discussion and may be implemented sometime soon by the network suppliers. This stuff, announced earlier this year, published in August, solved now. Right? So if the network operators, and this is again emphasizing this risk view, see risks for themselves, they'll act extremely strongly. If they don't see risks for themselves, they'll say something like, we are working on it, it is expensive, it's a long time process, there's no way of solving it quickly. Right? Nobody will ever say we don't care, but that's basically what they're saying. Right? That's a good question. So I guess what you're saying is it got solved quicker because it's much simpler to solve, whereas the other one involves many more people. Yeah, and that's actually not the case. The effort, at least estimated from the networks that we work with, is the same order of magnitude. Tens of millions. It's not cheap to solve anything like this if it involves this many customers, but on the order of tens of millions, right? Either one. And one got solved, the other didn't. Now, speculating a little bit here, nobody speaks openly about this from the industry, but I think this is easily explained by the risks behind here. The risks that we have with SIM cloning and with SMS fraud, they immediately and directly target the revenue of an operator, right? They lose money. Whereas the risks around GSM, they're more bared by the user of GSM. It's privacy risks. And if with the SIM attack, we could intercept calls and track your location, but nothing else, my estimate is it wouldn't have been solved. Right? Perhaps as an advice for researchers, and we tried this once successfully here and once not successful with GSM, try to emphasize the risks that are bared by the industry. All the research I'm reading on privacy is great, phenomenal, but it's irrelevant for industry. Try to throw in at least one other risk that they care about. And we tried this with GSM when we said, not only can we intercept calls, also we can steal the key and then start a new transaction and use that key in the new transaction and send an SMS. So we coupled a privacy problem with a revenue problem. Guess what? That revenue problem was solved within 6 months. They now change the key for every SMS that's sent out so that you can't recycle an older key. Do they change the key for every SMS that comes in? No. Right? So your privacy is still at risk, but when it does target their bottom line, they're very quick at solving it. Right? And maybe in your research you can find ways of making it painful for them to solve, and also solve it for everybody else because it's a privacy problem. But having both emphasis is important here. let me contrast this with one other example, just to show that, how it also can go. And I don't by any means mean to say that this is bad research. It's great academic research, but it is academic and only academic. And that is the result that 3G is broken as well. They sometimes call it A53, but it's actually called something different within 3G. So that encryption cipher was broken academically a couple of years ago, and it got good press. And there was a result where somebody looked at the algorithm, and I noticed that if you have key stream out of this algorithm, you can derive the key within 2 seconds. And I needed a certain amount of key stream for this to work, right? And then they derived the conclusion that that would mean that the application that's using this encryption function is broken. However, 3G takes data and it chops it up into tiny segments and then encrypts each of them individually. It never produces the amount of key stream that this attack needs. Now, that's not to say that the cipher is safe, but nobody knows how to break it in 3G. So there's no real-world risk. Perhaps the one risk that this research does bear is that people say, well, if 2G is broken and 3G is broken, it doesn't matter which one I use. And that would be, of course, a terrible conclusion. 3G is, from my understanding, not interceptable right now. If you switch your phone to 3G only, the only people intercepting you is your own telco and the people working with them, but not everybody else, right? So just as an example of how things can go. And the next person to look at 3G security now, of course, has this as a great burden, right? Everybody will say, well, it's already broken. How do you want to publish anything about it, right? If you Google for it, it is insecure. Even Wikipedia says it is insecure based on this result, right? And I think that's somewhat ridiculous. All right then. So I hope I convinced you that that it's important to keep in mind who wants to break something and how they abuse vulnerabilities to create a risk model. However, to get it done, get it fixed, you'll also have to emphasize how it hurts the people who are in a position to fix it. And that's the part that may not be academic research, but perhaps that's the part that the press most often misses when they take academic research and present the results as if these were world changers. Right? I hope this was confronting enough to have a good discussion now. Perhaps I stepped on a couple of people's toes, and that was intentional. So I'm looking forward to your questions.